And we are back. This is Module 2, Take 1, exam review video. Starting at problem number 7, and away we go. A table size of, there we go, m equals 1. It has 125 keys and 12 chains. Though that 12 chains is bogus information, doesn't matter how many chains are empty or filled or used. In the hash table, we calculate load factor with n, the number of values in the hash table, and m, the capacity, the number of slots in the hash table. It is n over m, and so the answer to problem 7 should be any of these types of numbers. Pro 8 and 9, I think that's all, work with hash tables that are what? They use chaining for collision resolution. They have a maximum load factor alpha of 0.75, which is 3/4. Keys are non-negative integers. Hash codes are equal to the key value. Tables double in size when they need more space. Problem 8, we insert the value 26 into this table. Where will the key be placed? Well, the first question to ask is, will inserting 26 push us over the load factor? Because if it does, then we need to grow the table first. So there's 4 elements in the table right now. N equals 4. There are 0 to 7, so that's 8 is the value of m. So we're going to add one more. 4 plus 1 is 5 over 8 is less than 3/4, so we don't grow this table at all. It's safe to insert the number 26. Where does it go? 26 mod 8. It's 26 minus 24, which is 2. Problem 9 is similar, but different. In this case, we are inserting 14 into this m equals 8 table, 0 to 7 slots. But there are already 6 elements in it. 6 over 8 is 3/4. We are at the load factor for the table. Adding one more, 6 plus 1 over 8 will be more than 3/4, so we have to grow the table. The problem stipulation says the table doubles in size when it grows, so we go from m equals 8 to m equals 16. Where will the value 14 be inserted? Which slot will it go into the table? Well, now its final destination will be 14 mod 16, which is just 14. Okay. The next question has to do with open addressed hash tables. Again, non-negative integers. We're making it simple, easy. Shouldn't say we're making it easy. I appreciate this question was probably difficult for not a small number of students. But we're not trying to trick you up with, crazy negative values for keys. Hash codes are equal to the key value, so the identity function. Both tables start at size of 8 and permit a maximum load factor of 0.75. 1, 2, 3, 4, 5, 6. 1, 2, 3. There are 6 values in the tables right now, so they are at load factor, and that's just fine. The first table, A, uses linear probing with the probing function f of I equals I. Table B uses quadratic probing with the probing function right here, I squared plus I over 2. I have written down some helpful values of this function. For I equals 1 through 5, I squared plus 1 over 2 goes 1, 3, 6, 10, and 5. So this question gives you a candidate sequence of values inserted into the hash tables in a particular order, and asks you to determine if that particular insertion sequence could have generated the hash table in these states? And if not, which one does it not work for? So for problem 10, see if I can get all this on the screen. This is not going to be fun, actually. That just occurred to me. For 11 and 12. For the linear table, I'm going to do some erasing too, because this is going to get ugly. Okay. For the linear table, we insert 24. 24 mod 8 is 0, so that goes in, and there it is. 22, the next value is 22 mod 8, which is 6. 22 is at 6, so all is good still. 7 mod 8 is 7. That's where the 7 is, so we're still good. It looks like this sequence, we're now up to have inserted 7. It looks like so far this sequence could have produced table A. 31 is the next element we're going to insert. 31 mod 8 is 7, but this has a collision because 7 is already in the table. Notice it's highlighted green up here. So in linear probing, we're going to take that cell or slot that it would have gone to. We're going to add on sequential values of the probing sequence until we find an empty slot. All of this mod 8. So for linear programming, we're going to add 1. Mod 8 is 0, but 0 is filled with 24 right here. So there's a collision there. Then we add another. 7 plus 2 mod 8 is 1. But and 1 is empty, so we can put 31 in it. So we have found the correct resting place for 31. So far, this sequence still works for the linear table. 10 mod 8 is 2. That's the next element we need to insert. 10 mod 8 is 2. That's where the 10 is. 6 mod 8 is 6. But there's a 22 there. There's a collision. So we probe 6 plus 1. At 6 plus 1 mod 8, we get 7. That's already filled. 6 plus 2 mod 8 is already filled with 24. 6 plus 3 mod 8 is what? 9 mod 8. That's 1. That's already filled with 31. 6 plus 4 mod 8 is 10. We've already put 10, actually, the value 10 into the table. It's at slot 2. So there's a collision there. Finally, 6 plus 5 mod 8 is 3, and that's where 6 lands. So this sequence could, in fact, produce the table A with linear probing. For quadratic probing, you'll notice the first several steps are the same as linear because and as we go through this, you'll see what I mean. For quadratic, 24, 22, and 27 are the same as linear. How do I know this? Because they didn't require any probes. Yeah, they just landed into their home slot, nice and easy. The first one we had to probe with was 31. So you'll notice that 7, 22, which one? 24. For the quadratically probed hash table, these values land same place as in the linear table. Everything is good so far. 31 was the first value we had to use probing for in the linear hash table, and likewise it's the first one for the quadratic hash table. 31 mod 8 is 7. There's a collision there. 7. So now we add to the value 7, the slot it should have gone to, had the table been empty, for instance. We now add to that successive values of our probing function. The first value we add is 1, which is just like in linear, and it's got a collision at 0, which is, 24 is there. 7 plus 3 mod 8 equals 2. Why is this a 3 and not a 2? Because we're on the second probe, and the value of the probing function is 3. So 7 plus 3 is mod 8 is 10 mod 8, which is 2. should, now it should be empty because none of the slots we've used so far, 0, 6, 7, those are the ones same as linear. And then where did, oh, right, yeah, 0, 6, and 7 were the only ones used. We've probed to slot 2. This is where 31 should land, but in the quadratic table, there's not a 31 in slot. Whoa, what am I doing? I need to use red. There's not a, now you can't read it. Yes, the value at slot 2 is not 31, it's 10. So this insertion sequence could not have generated the quadratic table. So for problem 10, we were looking for linear was okay, quadratic was bad, and the explanation that most people used was 31 should be in 2, and it's not. You could also phrase this in different ways. You could say 10 would have to be entered into the table before 31 because 10 is the one that 10 is in the table that we're trying to match. Any of those, as long as they were correct, any way of stating this, as long as it was correct, is sufficient. Okay, do some erasing here. It's going to be a little problematic to do these other problems on my screen with the tables up there. Okay, we'll just suffer. 10, 24, 22, 7, 31 linear insertions. 10 mod 8 is 2, so whoops, not in red. There we go. Sorry. So 10 mod 8 goes into 2. 24 mod 8 goes into 0. 22 lands in 6. All of these are so far good with the table. 7 mod 8 is 7. That one's good. 31 mod 8 is 7. There's a collision. We add 1 for linear. 8 mod 8 is 0. There's a collision. 7 plus 2. Add 1 more. 9 mod 8 is 1. And that's where that works. So the 7 can go into slot 1. And I believe, let's see, 1, 2, 3, 4. Oh, sorry, 5. Not the 7 into slot 1. 31 goes into slot 1. And that's okay. This actually describes this table as we see it. Does it? Wait a minute. I forgot to write down the addition of 6 into the table. My apologies. I did not show the insertion of 6, that 6 works for the linear, and when I was writing this out, I was distracted by way too much conversation. In the environment I was in. So let's just figure it out. We've already inserted 24, 31, 10, 22, and 7 in the hash table. All those have landed in these particular slots. So far the insertion sequence is fine. What happens when we add 6? Well, 6 mod 8 is 2. 6 mod 8 is 6. That's already filled, so there's a collision. We add 1. Chose the 7. There's a collision. We collide there, we collide there, we collide there. Finally, after adding what? 1, 2, 3, 4. On 6 plus 5. On 6 plus 5, mod 8, we land at slot 3, and we finally put 6 there. And so the linear works. I just want to point out, I just said 6 plus 5. The 6 I was adding 5 to was this 6, not the value 6. I was adding it to the slot where the value 6 would have gone in an empty 8-slot table. Okay, now we can move on to quadratic. Alrighty. Quadratic for this very same sequence, well, it will be the same as linear until we hit a collision. So we get 10 goes to 2. So the result is the same as linear for 10, 24, 10, 24. Oh, I'm yellow now. 22 and 7. The first conflict is at 31. It has a conflict because slot 7 is full. We add 1. Where did this 1 come from? This 1 came from right there. It's the result of I squared plus I. There should be a dot up there. Here's the equation. Over 2, because we're doing quadratic probing. That has a collision. 7 plus 3. Why do we choose 3? Because it's the I equals 2. We're on the second probe, and so we're adding 3. 7 plus 3 is 10. Mod 8 is 7 plus 3 is 10. Mod 8. Another typo. Oh, I love it. This is a 2, which already has the value 10 in it right there. Yes. So just to highlight that nobody's perfect, that should be a 2. After adding 3, we're on the third probe sequence. So we add 6. 7 plus 6 is 13. Mod 8. This one is correct, I'm sure, is 5. And that's where that is available, and that is where the value 31 is going to go. Is that inside the table? Yes, there it is. Happy day. I believe we're down to yes, the last insertion, so which is 6. So we've gotten all of these in. Okay, what happens with 6? 6 mod 8 is 6. That's full. Yes, it has 22 in it. 6 plus 1 mod 8 is 7. I knew that. There's a collision there because 7 is already in our table. The value 7 is already in our table at slot 7. And then we're doing quadratic probing, so we go to 6 plus 3, which is 9. Mod 8 is 1. Ba-boom. That's where the 6 is. So this particular insertion sequence works for both tables. Okay, one more to go. Will I make it? I don't know. You know, just to rub it in, Hellman. Leave that red mark on the screen. Just in case you start thinking you're too good. All right. Clear this out. Clear that out. There should be a dot right there. Now I feel better. I know, it doesn't take much. See above for, what am I doing reading the instructions? Okay, now we're going to insert the sequence, the same 6 values in this last sequence, 7, 22, 6, 10, 24, 31. Let's do the linear one first. 7 mod 8 is 7. Here we go. So 7 goes into slot 7. 22 mod 8 is, yes, 6. So 22 goes into 6. That one's okay for the table up above. That's what these little check marks mean. 6 mod 8 is 6. Yes, that's true, but there's a collision. Why? Yeah, because we just put 22 into 6. There's a collision, so linear probing, 6 plus 1 mod 8 is 7. There's a collision there. 6 plus 2, so probe the next location, 6 plus 2 mod 8 is 0. Yes, that's true. Have we used 0 yet? We've used, 7, 6. We've only used slots 7 and 6. Yeah, we are inserting the value 6. We're on the third element. 6 plus 2 is 8 mod 8. It should go into 0, but, oh, look at that. The 0 slot for table A has the value 24. So it doesn't work for linear. It is broken. Many students said 6 should be in 0, which is perfectly acceptable. Some students said, what is there, 24? That 24 would have to be inserted before 6. Either of those, of course, are acceptable ways of saying it. Well, anything that is correct is an acceptable way of saying it. For quadratic, right, 7 and 22 are going to be inserted just like linear. 6 mod, we had our first collision with 6. 6 mod 8 is 6. We know that's a collision. 6 plus 1 mod 8, we know this is a collision as well. It happened right up there. So that first probe value between quadratic and linear are the same. So we've essentially already done this work. But now things change. Second probe value for quadratic is 3, so 6 plus 3 mod 8 is 1, and that's where the 6 should land. And in fact, in the table, that's where 6 is, so all is good. I should also point out now, because it just occurred to me, that the most common mistake I saw for students using quadratic probing was that they weren't taking, for instance, 6 plus 3 mod 8. They were just saying, I'm going to look at the slots 1, 3, 6, 10, 15 mod 8, and it's going to go, and the value is going to go into the first empty slot. And that is not the way quadratic probing works. All probing uses probes from the initial slot where the element would be if the table were empty when it was being inserted. Okay, 10, the fourth element, 10 mod 2 equals 2. That one is not a collision, and it works with the table above because I got a little check mark there. 24 mod 8 is 0. That works. 31 mod 8 is 7. That's a collision, so we do quadratic probing. 7 plus 1 is 0, but that's a collision. 7 plus 3 is 10. Mod 8 is 2, but that's a collision. And 7 plus 6 is 13. Mod 8 is 5. And not only is that not a collision, but it's also the value in this table at slot 5 is 31. So it works for quadratic but not for linear. Man, those are tough questions to review. That's just, if I say the word mod again in the next 5 minutes, watch me have to. Excuse me. In case you wonder why I don't edit my videos, it's because I hate video editing. I've done it in the past. Don't need to do it anymore. All right. Problem 13, and if I'm not mistaken, this is the last problem of Module 2 and the last problem of this video review. We have a hash table using open addressing and double hashing. I want to make sure I'm not on red here. Double hashing. Hash table starts at size 4 and doubles in size as necessary to maintain a load factor of less than 0.5. Regardless of the primary hash function, would the secondary hash function, because we're using double hashing, the secondary hash function of x mod 13 be a good choice for this hash function? Good choice of secondary hash function. Justify your answer. What do we want from secondary hash functions when they're used in open addressing? I can't think of where else they're used. Secondary hash functions used in open addressing with double hashing. What properties do we want? You want the hash2 to never have 0 in its range. So it cannot produce the value 0. Why is that? If we roll back to the previous one, when we're doing the collision resolution, and adding on multiples of that hash value, if we're adding on multiples of 0, we'll never change. We'll just, we'll get a collision at 7, and then we'll test 7 plus 1 times 0, and that'll be 7, and then 7 plus 2 times 0, and that'll be 7. We'll never check any other table slots. So that would be a bad idea. We really don't want 0 in the range. Also, we want all the possible outputs of the hash2 function to be relatively prime, or what they also call co-prime, to the table size. And this is because if you have a double hashing result, which is not relatively prime to the table size, you can end up checking a very small minority of the tables and simply cycling around that loop, as it were, cycling around those slot indexes. And if they're all filled, you have an infinite loop, and your hash insertion function is going to fail. And why? Because you got a bad hash2 function. So we want all the outputs. So notice that the first criteria is we're concerned about just one of the output values, and that it's not 0, or I should say any of the output values, and cannot be 0. And by any of the output values, what I mean, for all the possible x's that can go into the function, the hash2 function can never generate a 0. And all of its outputs need to be co-prime to the table size m. All right, well, so this hash function, it turns out, is not very good. So the big first answer to problem 13 is no, this is not a good choice for secondary hash functions. Let's look at why. Because this expression can be 0 for any multiple of 13 as the input. So we don't want that to be the case, and this is a bad hash2 function. Additionally, the outputs, it will have outputs in the range of what? Well, this will be x mod 13 has the range 0 to 12. So we know that 0 is bad, but we'll also have all these even numbers in its output. They all have a factor of 2. They're even. And that means that they're not co-prime to the table size, which always has a factor of 2. We started out at 4, which is 2 times 2, and then we double it every time. So m can be expressed as the power of 2, which means it's got a factor of 2 in it, and that means that the outputs of hash2, they are not all relatively prime to the table size. This is why for open addressed, double hashed tables that have power of 2 sizes, we prefer hash2 functions, that create odd numbers, because odd numbers aren't even, and therefore they don't have a factor of 2. Bada boom. One thing that tripped people up on this question was they considered the function hash2 of x as the qualities for the primary hashing function for a hash table. This is not the same. There's different sets of properties, qualities, for the primary hashing function versus, a double hashing function. I really apologize for that. The primary hashing function, what properties do we want? We want it to cover all of its range, possible values of range in the way of number of bits it can generate. We want it to cover that great big spread as much as possible. We want it to take nearby values and separate them out very far. We want it to use all of the input for the of what it's hashing. So, for instance, use all of the string, not just the first 2 characters. And what's the third thing we want? We want its distribution of values in its range to be essentially uniform over the width of its range, if you will. We do want hash2 functions to use all of the input as well, but that's certainly not a failing quality of x mod 13 because it uses the entire value of x. This has been Module 2 review for take 1. Thanks for hanging out. I'm going to stop this video.